Hi, I'm Kevin. I'm Hunter.
I'm Will.
I'm Michael.
And I'm Caroline.
And we're Team RobERT from the University of Georgia.
Go Dogs!
Our team is a multidisciplinary group of students in the University of Georgia College of Engineering, with a roughly equal split of mechanical and computer engineers. From last year, we recruited most of our current team, with half of last year's members acting as leadership for this group, and the other half acting as leadership for another submission from the University of Georgia. Our aim for our submission was to finish the course in the shortest amount of time by completing the task for each row simultaneously. We accomplished this using an expanding chassis design, which drives apart using our 4-wheel steering drive system. Our system does precise course correction by following the provided black electrical tape using the bottom-mounted camera and OpenCV. The seed depositing is handled by our fully mechanical dropper system, which interfaces with each plant and drops a seed depending on its geometry. The mechanical dropper is also used to capture images for our vision system, which uses a machine learning approach to classify each of the plants as stressed, unstressed, or non-germinated. The result of our hard work is the robot platform we like to call RobERT. While a little rough around the edges in some areas, we produced something that we are quite proud of.
The final phase of the mechanical design was based around an expanding chassis that was designed to scan and process all 4 rows in a single pass. To deploy, the mechanism simply drives apart until the locks close, preventing the sides from drifting together. The center section is suspended in the center lane with drawer slides. Our movement system was integral to being able to open our design without the need for extra actuation components. This reduced weight and simplified the overall robotic design. The mechanism is able to scan all 4 rows by driving the near side panel to the second black line, driving the other side panel to the 4th black line, and suspending the center section above the 3rd black line. The frame for the robot was made from laser-cut acrylic, which allowed for a lightweight chassis that was fully customizable and had plenty of space for electronic components. The dropper system was developed to be able to differentiate and target the open spaces while avoiding fully grown plant. It is designed to drop only 1 seed at a time by utilizing a series of cylinders to keep the seeds in line. Many iterations were made in order to improve reliability, decrease the weight of the robot, and improve the precision with which the seeds were dropped. The droppers were 3D printed from PLA filament with minimal infill to reduce weight and allow full mechanical design customizability. These droppers save time for our overall robot by ignoring the need for the robot to know what kind of plant it is before it drops the seed. The 360-degree steering system is based on the driving concept utilized in Mars, a prototype agricultural robot currently in development at the Biosensing and Instrumentation Lab here at UGA. It uses 2 motors for each wheel, one for controlling wheel direction and the other for controlling wheel speed. This allows the robot to strafe in any direction needed at any point in time, as well as enabling the robot to turn on or off axis at any point.
In order for the robot to follow along the electrical tape, our first step was in identifying its edges. Since the 2 shades, black and white, are opposite on the color spectrum, we had an easier job in determining where the tape is. At this point, we could have decided to utilize packages in OpenCV that can detect edges in the frame, but this method would not give us access to the individual points along the edges of the tape, making our calculations inaccurate. Instead, we decided to analyze the tape in terms of individual pixels in a wider shade range so we could distinguish individual points on the tape. This method made determining the angle off of the center line more accurate, as we only needed 3 points with little approximation. We utilized a separate OpenCV package to approximate the shape of the tape using the edge data already collected, making our calculations even more accurate.
Our robot compares its current and desired heading to determine what corrections are needed. We initially wanted to use Ackerman steering, as it would have allowed us to perform angular and lateral correction in one operation while continuing forward motion. However, physical limitations made implementing Ackerman-like behavior difficult without changing the design of the robot. As a result, we split heading correction to 2 parts, angular correction and lateral correction. Angular correction uses center axis steering. This means the robot must stop moving forward and turn the wheels normal to the center of the robot to rotate the body. We find the error in the current angular heading of the robot with the bottom mounted camera. The error is fed into a PID controller. It generates a correction angle to fix the heading with little overshoot to reduce the impact heading corrections have on course completion time and seed dropper positioning. Lateral correction is done using 4-wheel steering. We find the resultant distance and angle needed to make the robot coincident with the electrical tape based on the error and lateral position. The robot can move all 4 of its wheels independently, allowing us to maneuver the body without changing the angular heading. Since lateral correction does not induce torque on the robot body, we are able to maintain some forward motion while correcting.
Classifying each germination position on the competition board was broken into 2 distinct tasks: capturing and pre-processing images for each position, and constructing a reliable way to use that image data for detecting germination status and plant health. OpenCV allowed us to programmatically capture and edit images taken by the cameras on the robot. To reduce misidentification, we cropped the images to only include the target germination position. To reliably detect when to take a picture, we utilized the existing mechanical dropper design along with a dynamic motor to create a spring-like trigger system that would capture an image once a set force is applied to the mechanical dropper. When this force is no longer being applied by the plant stalk, the dropper moves back into position to detect the next plant. We did this by utilizing some of the smart actuator capabilities of the dynamic motors, one of which is a readable present load value which represents the electric current through the motor at that time, making it useful as a torque sensor. The detection software uses the processed images from the cameras to classify each image by germination status and/or plant health. Initial efforts to accomplish this used a simple OpenCV script which would count the number of yellow, green, and white pixels in an image and output that as a percentage. This worked well enough in simple cases, but occlusion of the target crop made detection inaccurate. While we could have developed more advanced computer vision techniques using OpenCV, we decided to use a machine learning approach as we had an interest in learning it. Using TensorFlow, we developed a convolutional neural network to classify each germination position as green, yellow, or open for healthy, unhealthy, and non-germinated positions respectively. To collect the data required for training our neural net, we generated random competition boards using the competition GUI script and took 10 pictures of each position on the board, rotating the plants slightly between pictures. After doing this a few times, we split our dataset into training and validation sets with a 1:4 ratio, with the training set being used to train the neural network and the validation set being used to test its accuracy. We then trained the model for 1500 epochs or training sessions where we achieved 99% accuracy on our validation set. As Python is one of the fastest languages for rapid software prototyping, we chose to use it for initial design of all software. We planned to rewrite the software in C++ after functionality was finished, but due to time constraints and the inability to meet in person regularly, we resigned to stick with Python. Because of the nature of interpreted languages such as Python, having a true state machine would have significant performance impacts. For this, and to more easily integrate all of our software systems, we leveraged parallel programming using the Python multiprocessing module. We tried to first use the Python threading module, which enables a developer to have separate threads, or pieces of code running concurrently on the same Python interpreter. After further testing, we saw that threading would still be very slow, as Python has something called the global interpreter lock, which locks code execution on one thread at a time. It was at this point that the team turned to using Python multiprocessing module, which allows all of the subsystems to be executed in parallel, providing the modularity and performance we were looking for. Some of the functionality of the robot requires the separate processes to communicate. Fortunately, the multiprocessing module has solutions for this, implementing easy-to-use wrappers for the standard pipe and shared memory APIs provided by the operating system. To effectively coordinate the various subsystems, we organized them into a class structure, with each class having a constructor, any helper methods it may need, and a run method, which would run code in separate processes or threads if need be. This class structure shines when the team started thoroughly testing the platform's subsystems, as all they had to do was import a module's respective code, set up any extra imports or code, and set up the multiprocessing and run the systems in question. This made independently validating all of our software a simple endeavor, and it ensured that it would be executed in precisely the same way, no matter if it was a test script or the actual robot bring-up script.
The parallel nature of this robot requires many systems to work together in unison with a very tight tolerance to fully function. All systems and subsystems were able to be designed, fabricated, and mounted even with current events leading to some undesirable delays. With individual subsystems having differing success probabilities, the overall system reached a start-to-finish final accuracy of slightly below 50% in procurement of all possible points for the competition. We hope you found our robot as interesting as it was to build, and thank you very much for your consideration. Stay safe out there.